does that automatically. So like it'll migrate stuff onto the fast storage, and then when it sees this and it's using it, it migrates it back on.
So welcome to the afternoon session. It's a pleasure to introduce Zehua Lai, who is at the Department of Mathematics, and he's going to talk about expressive strength of ReLU-transformers.
Yes, so thank you for the invitation. Today, this talk, I'm going to talk about one written work that I did about ReLU-transformers, and this is a joint work with Yutong Liu, who is a PhD student in Georgia Tech now, and currently my PhD advisor in University of Chicago. So let's start with the introduction. So the main focus of this work is about the transformer. The transformer underlies many modern AI applications, especially in all kinds of large language models. So this is the original attention is all you need paper. This is the graph I directly copied from that paper, and this is somehow this structure defines so-called transformer. And I will give you the precise definition shortly. So here is another graph that I copied from ChatGPT paper. So this is also like this left-hand side is also a structure of transformers, and this is another graph that I copied from AlphaFour paper, and this is used to to predict so the input would be like a sequence of amino acid information, and then you can predict how the protein folds in 3D dimensions. So and then this neural structure is also called transformers because it essentially uses the same core ideas. And so how to understand the structure of transformers mathematically? So let's start to give you the definition. So first of all, let's introduce what's traditional fifth-order neural network. It's defined by a bunch of compositions of ReLU of ax plus b. So it would be an advanced function, and then composed with entry-wise ReLU, and then composed with an affine function, and then composed with entry-wise ReLU. And then we draw it like this, and then each node corresponds to 1 dimensions. And then if we have like L compositions of ReLUs and affine functions, we will call this L to be the number of layers of this neural network. And for this traditional fifth-order neural network, there's a very famous theorem that says that every neural network is a piecewise linear function. So it means that we can find a partition of the space such that each piece is a linear function, and it's continuous on the whole space. And then conversely, if you are given a piecewise linear function, you can actually write down a corresponding neural network. And this neural network has at most log n depth. So n is the dimension of the space, and the y's can be bounded in terms of the number of affine pieces. So we can give you a bound of how many parameters we need to use to represent this any piecewise linear function. So we can maybe there are a lot of works that they try to understand the complexity of piecewise linear functions using the number of parameters that you need to represent the function. And then this is also studied extensively in using the methods from tropical geometry. It's called piecewise linear functions are called rational tropical functions. And as a corollary of this theorem, we can approximate any function in C0 arbitrary well for a compact set, in a compact set. So this is just because that you can just do linear interpolation. So this is a very classical result. And then our goal is to do similar things for transformers. So a transformer is defined by this, contains the basic building block of transformer is called attention module. So an attention module is a map that composed with, that looks like this. So there are three maps, V, K, and Q. Those V, K, and Q are all affine maps. So they are all given by some X plus B, X plus B, X plus B. And those three affine maps are composed in this way. So it's V times Somax times K, Q. Here, we need to care careful about the dimensions. So all those, so X, the input is N times P. And then this P would represent the length of a paragraph. It's the, if you try to use ChatGPT, it's like the tokens. So it's the length of the sentence you can give it. You can give to the AI bot. And then this N would just be some abstract vector embedding. And this Somax would be performed column-wisely. So this would somehow, so you can somehow understand this whole thing as some kind of attention mechanism that try to, this Somax is gives weights to different positions in a sentence, and then as a result returns you with a new sentence. Now, so the most important hyperparameter in this attention module is P. Okay? This P is usually some predetermined P, but other hyperparameters N and M and D are something that you can tune, you can fine tune. We will consider a simpler version, where we are not using Somax on each column. We use ReLU on each entry. Okay, so we have three affine maps, and then we take the product of two affine maps, and then we do take max x0 on each entry, and then times V. So if we do this, we get this thing, we call this thing ReLU attention module. And we can also do so-called multi-head attention. It means that we can stack multiple attention modules together vertically, so that we get still keep this dimension P, but vertically we can make it very, very high. And then the final transformer would be a composition of attention modules, multi-head attention modules, and neural network. So we can do one multi-head attention, and then do one neural network, and then do one multi-head attention, and do one neural network, and so on and so forth. And then we can get maybe this would be a T-layer transformer. Okay, we call it a whole structure transformer, or sometimes we call this encoder. Yep. And there is also a earlier result that says if we consider the Somax encoders, we can approximate any function in C0 norm arbitrary well in a compact set. So this kind of universal approximation also holds for Somax encoders. And now let's try to understand the case of ReLU encoders, ReLU transformers. So ReLU transformers are easier to understand because now all the operations in our definition is just multiplication, addition, and maximum. Because ReLU is just maximum of x and 0. So we will call a function that can be generated by those operations a max definable polynomial. Okay, so it's not so a polynomial is generated by plus and multiplication, but now we add one additional operation, the maximum. This notation is probably not standard. Some people call it like supremum, infimum definable functions. Some people call it other using other terms, but we stick with this term here. And then if we have a function, if we have a max-defined polynomial, it must be a piecewise continuous polynomial. Okay? And this is also called splines. So we have a function that you can cut it into, find many pieces, and in each piece it is just a polynomial. And then we call the cuts. The cut is usually not a linear cut. It's not a linear partition. It's usually a partition by polynomial. So this is called a semi-algebraic partition. Now, there's an identity that says if we multiply f and then ReLU of g, then this equals to max of minimum of something and then something. Okay. Now this identity means that if we have multiplication outside of maximum, then we can exchange the order and then put maximum outside of multiplication. Okay, you can see in the left-hand side we have first maximum and then multiplication. On the right-hand side we have some multiplication and then maximum and minimum. So using this, we can move all maximum outside of multiplication. So if we do this, you can do an induction and prove that any maximum function can be reduced to a easier form, that is this maximum and minimum of a bunch of polynomials. Okay. So you have a form that's easier to understand. It's not any arbitrary composition. It has a very somehow easier canonical form. And there's a conjecture called the Pierce-Beekhoff conjecture. And this conjecture says that if I give you a spline, a piecewise continuous function, then there exists some polynomials such that this spline can be written as max minimum of polynomials. So this conjecture simply says that max definable polynomials are piecewise polynomials. Okay. Now this conjecture is very easy to state and easy to understand, but it's actually very hard. It's still an open conjecture so far, and we only know some very special case. For example, if we know this spline, this piecewise continuous polynomial is actually linear, it's a piecewise linear function, then we already know this is true. We already know that each piecewise linear function can be written as maximum of minimum of linear functions. This is already known. And also, we also know that this is true for splines in a plane. Okay, in dimension 2, this is true. Okay, but for higher dimensions, we don't know if this is true or not.
I think you have the wrong citation there. The piecewise linear function is of Chinnikov.
Yes, you're probably right. Yeah, I probably said the wrong one. This is much earlier. This should be much earlier. So we have proved a theorem that says we can prove a theorem that says that we can, first of all, we can show that each encoder is a max definable function, which is just by definition. This is a trivial direction. But conversely, every max definable function can be represented by an encoder. So those addition, multiplication, and maximum, those operations can be like, you can use encoders to represent all those operations. And of course, if the Pierce-Beekhoff conjecture is true, then every spline, every piecewise continuous function, piecewise continuous polynomial can be represented by an encoder. So we have a theorem that somehow characterize the class of ReLU encoders, ReLU-transformers. Okay, but of course this relies on an unsolved conjecture. Yep.
What do you mean by encoder? Because
It's the transformer. I use those two terms interchangeably. It's this thing. Okay, it's a bunch of attentions, and it's a composition of attentions, and then feed-forward neural networks, and attentions, and then feed-forward neural networks, and so on and so forth. We call this thing an encoder or a transformer.
But they have a term decoder, only generative model.
Yeah. There's another thing called decoder that has additional structures. Yeah. So we did discuss that in the full paper, but I don't want to make the talk more complicated than what it is right now. But this is already this is already a pretty good result, because this already implies approximation in any CR norm. Okay, because we know Pierce-Peikoff conjecture is true in one dimension. It's true in the plane, and it's true in one dimension. So it says that any univariate spline is mass-definable. And then, of course, we can construct a bunch of multivariate splines using univariate splines, and then use splines to do CR approximations. Okay, so this is not something very hard to do. And also the conjecture is to be tricky in that even if the conjecture is true, if we know that if we have a spline that is defined by polynomials of degrees bounded by k, piecewise d, and then we somehow write it in this max minimized form, then the degree of all those polynomials here can be larger than k. Okay, we don't have a good bound on a degree here. So even though maybe for each pieces in F the degree is less than k, the right hand side may have a degree larger than k. Okay, so this means that we actually want some effective version of this conjecture, so that we can bound the number of parameters we use. Okay, otherwise, if we don't know the bound for right hand side, we have no control over the parameters, over the capacity. So now let me talk more about the Pierce-Peikoff conjecture and how it is proved, how we can prove this conjecture. So a possible way to prove this conjecture is as follows. So if we have a piecewise polynomial f, and then if there are two semi-algebra set A and B, and f is locally given by two polynomials G1 and G2, and then let S to be the set of polynomials H, such that H is non-negative in A and then non-positive in B. Okay? And then we let this bracket AB to be the ideal generated by S. And this ideal is called the separating ideal. It's the ideal generated by polynomials that can separate the two pieces. Okay? If there's a theorem that's called a separation theorem, that says separation conjecture maybe, that says if for any AB in this partition, we have this G1, G2, the difference between two pieces is inside of this separating ideal, then F is max definable. Okay? So we do have a more algebraic condition to make sure that to prove the hard directional Pierce-Peikoff conjecture. And more generally, you can define this for two so-called prime real idea So if alpha beta is two prime real ideals, you can somehow also define a separating ideal, but that's quite abstract and it's not very useful in practice. So we will use this semi-algebraic sets definition of separating ideals. And this basically means this. This theorem basically says that if you have a polynomial that separate A, B, and then somehow and you have like G1 and G2 at two pieces, and then that polynomial can help you like cut out the part that you don't want and leave the part you want. So basically, as long as you know this thing is in the separating ideals, you can directly explicitly write down a polynomial, a max minimum something that give you this f. Okay. And there's so let me give you the proof of Mark in for the D equal 2 case. So he proved that the Peirce-Birkhoff conjecture is true in dimension 2. So the proof roughly goes as follows. So we only need to consider the case where two pieces, two semi-algebraic sets are open. And if they do not intersect, then the separating is true. So we do have this condition is satisfied. This is because this comes from positive stanzas in real algebraic geometry. So this is already a hard thing to prove, but it's true. And then if some two sets intersects at the co-dimension 1 sets, in the case of plane, it's just a curve. If two semi-algebraic sets contact in the curve, then the curve is easy to understand. It's easy to understand what's a curve in the plane. It's defined by some polynomials, and we know how to separate two sets through a curve. And then if two sets intersects in a single point, that's also like topologically it's very easy because you can go around the points in one circle and then understand how the difference between how to separate the two sets intersects in a point. So this is all quite easy to do in dimension 2. Okay. Now let me talk about the final thing we proved, which is the linear partition case of Peirce-Birkhoff. So we actually prove that Peirce-Birkhoff in the case of linear partitions is also true. So if you have a linear partition of the whole space, meaning basically you have a hyperplane arrangement on the space, and then you have some piecewise continuous polynomial defined with respect to this partition, then this piecewise polynomial is max definable. Okay? So to prove this, we need to somehow prove again the separating conjecture, which says that the separating idea, which is ideal generated by hyperplane separating two closed convex polyhedrons, equals to the vanishing ideal of the affine span of their intersection. So if you have two convex polyhedrons, okay, and then maybe they touch in a plane, let's say, and then here we have a plane that's separating them, okay, and then you need to prove that all planes separating two convex polyhedrons, their intersection is the same as it's just this hyperplane. So I mean, if you transform the original problem to this, then this is almost a trivial problem. This is intuitively correct, and so we can actually cite a result from hyperplane arrangement. It says that if you have a hyperplane arrangement, then the intersection of hyperplanes separating two open chambers equals to the affine span of the intersection of their closure. Okay, so you have a very intuitively correct statement in hyperplane arrangement. And this is no easy proposition actually. The proof is quite long. It's in this textbook, and it's like 60 pages into a textbook, and you need all the prior definitions. But anyway, you can prove the you can find a proof in the textbook. So this tells us that linear partition case of Pierce-Bikoff is true. And then this directly give us an effective version. So now the effective version of Pierce-Bikoff says that if you have a spline and it's locally defined by polynomials with respect to some hyperplane arrangement of big N hyperplanes, and then this spline can be written as max minimum of some polynomials. And here the max and minimum, the number of f can be controlled by so this n prime is controlled by O n to n's power. So the number of f is we have some bound on number of small f KL we use, and we also have bound on the degree. So the bound is bounded by a maximum of GI and then 2 times GI minus GI prime. So it's so we have an effective bound, and this effective bound implies parameter bound for encoder differentiation. So we can actually say that if you are given a spline with some bounded degree and bounded number of hyperplanes, and then I can tell you that how many parameters you need to use to represent that spline. Okay, and we do have a concrete expression in the paper, but I don't want to write it here because it's quite ugly. It's just some long expression, long big O notation. So that's all for this talk, and thank you.
Any questions?
I mean, is there some hope to prove Pierce-Bikoff somehow with these?
So the clearest, the most clear path right now is still like using this, using to somehow prove this condition. But this condition seems really hard because, as we see that we can prove like the codimension 1 intersection. But if we have somehow a codimension 2 intersection, maybe in, let's say, in 3-dimensional space, then we have somehow a curve in a 3-dimensional space, and already that's hard thing to classify, okay, and that's even harder for higher dimensions. So we are actually like trying to do some kind of classification of all varieties somehow. So this seems like a very hard task. Yeah.
Okay, so I know that this work is trying to establish, what kind of functions, will come out from if you replace the softmax by ReLU, right? But if I recall correctly, in the transformer, especially the block of the P and Q, and then it seems that they claim that some kind of normalization is very important. You divide by a square root of something, I don't remember. They claim that it's very important.
Yes.
So do you have anything to say or insights about that normalization, or in your context?
No, like we also like ignore the normalization part because the square root of something is not
Right.
piecewise polynomial. So we just ignore the inconvenient part. But there is a paper that I can find that says if we replace softmax by ReLU, then they draw a curve of computational power against accuracy or something, and it behaves roughly the same in image classification, I think. Yeah. So ReLU-transformer is probably not much worse than softmax transformer.
If there are no more questions, then let's thank the speaker again.